Hey everyone, welcome back to the channel. I wasn't going to do a video on this initially, but I got to poking around in here and I thought well, maybe it might be worth taking a look at. So anyway, we'll have a look and see where we go with this. So this is an HP 334A distortion analyzer, and I think the only difference between this one and the 333A is that the 334A has the RF detector built into it. But anyway, it's a pretty popular HP distortion analyzer for making distortion measurements, among other things. And this instrument was one of the survivors from my lab flooded out a couple years ago, and I haven't really done anything with it since then. It's just been I took it and did some basic cleaning and just put it on the shelf for a while. But I figured I'd go ahead and get into it and start poking around. And as you can see, I've already gone ahead and making some disconnections here. But we'll look through the instrument real quick, and then we'll talk about what we're going to look at here on this instrument. So obviously, here's the top portion here. And underneath this board is the A2 board, which is the impedance converter and the meter circuit. And then on the side here is this is actually the bridge amplifier here with the bridge tuning network, this big capacitor and these resistors here for doing the bridge tuning. And I think this is these are the phase phase shifting amplifiers. There's a resistive detector and a 90-degree phase shifting reactance detector, and that's what these are here on this board here. And of course, this board back here is a power supply. Now, unfortunately, when I had this instrument before, it was sitting on the floor, and it was sitting in this position. So when the unit got flooded, of course, all the water went this way, and all of the sort of dirt and whatnot, when it settled onto this board, which is unfortunate because this is a very high impedance portion of the unit. And as you can see here, there's a very high impedance connections here. These little blue Teflon standoffs there for this very high impedance section here. And so I've had this board out and had it doing a lot of very careful cleaning with this board here to try to get it as clean as I can. And in the manual in particular, it talks about this board being sensitive, and it's sensitive even just to touching it with your hands, that the body oils from your fingers will get in on these connections that are in here, and in particular this portion right here. So it tells you to be careful when you're handling this board not to contaminate the board. And I've got it pretty clean now. And then of course, cleaned the rest of the instrument out. So all of the switches, of course, any of these horizontal surfaces, the rest of these boards over here on this side and the power supply board, they weren't really too bad because it's just the water would settle here. But now when I take this panel off here, of course, there's all kinds of silt and stuff down in this bottom portion here. And as you can imagine, before I cleaned it, any of these horizontal surfaces, of course, had a layer of sediment just laying on it. And there's still a couple of places in this meter that I haven't got to. In particular, down in that corner down there, you can see, I'll try to get a light down in there, but you can see there's still a little bit of, some dirt and stuff in there. So I haven't gotten completely into the unit to get it cleaned out, but, just kind of going it piece by piece and getting it cleaned out. So just going through, the instrument, just like I said, I had it before, and actually I never even really got a chance to use it. After I purchased it, it kind of went into a, I just had it sort of storing, and I never really got a chance to use it. So I don't even know how well it was working before the water for the flood damage. So when I started getting into this instrument, trying to work on it a little bit, I just basically went into the in with the manual and started with with the basic section here, which is the performance checks. And surprisingly, most of the instrument seemed to work pretty good. I didn't have too much issue getting the performance checks to come out right. As you can see here, we've got some measurements with the checking the voltmeter accuracy and frequency response. Had no problems there. Basically, I just went through working the through all the performance checks, and where I did start to notice that there may be some issues was when I got into the automatic nulling mode check. So what you do is you put a frequency of a particular whatever the test calls here. So for the automatic mulling or the automatic nulling mode check, it's going to look for frequencies at 5 kilohertz and 50 kilohertz and 500 kilohertz, and it has you repeat all of these functions here. And what I found was that the automatic circuit wasn't working very well to automatically null the signal out. And so that got me to looking into the photo or the bridge circuit. And the way that the bridge circuit works in this unit is in the rejection amplifier here, it uses a photoresistor network here in the rejection amplifier. As you can see here, here's our photoresistors and our bridge. So this black box has the photoresistors and the lamps that are driven by our those the control circuits right here for the bridge balance. That's what they call it, the control circuit and bridge balance here. As you can see, and here's the lamps that they are driving. And then there's a resistive control loop and a reactive control loop. So those drive the lamps to do the automatic nulling. But like I said, so it wasn't working. The automatic nulling wasn't working right. And I got to looking into, I initially thought, well, the unit was flooded out, so the bridge is probably dirty. The photocells are probably dirty, and the lamps are probably dirty. So I took the bridge module apart, and it was actually pretty clean inside. But what I did find was, so we've got a procedure here in our service manual for photoresistor check. So that's what we're going to check, because if the automatic null is not working correctly, then this could be the reason. Because like I said, the automatic null is controlled by this photoresistive network that's driven by our lamp driver circuit that is part of the control circuit. So that's the first thing I'm going to check, because I've already gone through the schematics, and I checked. They give you in these schematics, they give you voltages at the various points, and in the service manual it'll tell you the condition to put the instrument in, the switch to alignments to make on the front panel, so that these measurements can be made. And I've made these measurements, and I've got pretty close values on all of these. So I suspect that the circuit's working okay, and also there's some waveforms you can check too on some of these points here with these stars. There's waveforms associated with those, and you can look at the waveforms on the oscilloscope, and the waveforms look pretty close to the way they should look. So I feel like the circuit's working correctly. I think maybe the problem is just in the bridge, the photo the photocell portion of the bridge circuit. So we're going to take some resistance readings here. So it'll tell you here between the pins what the photoresistor values should be. So, so everything we'll do is we'll turn off the, well, I'll tell you turn the unit off and set the mode to manual. So we've got the mode switches in manual. And the frequency range to 1K. So our frequency range, we need to put that in 1K there. And disconnect all the wires on the A6 board except for pins 6, 7, and 8, which are the lamp driver connections. So we looked at those already, pins 6, 7, and 8, and those are still connected because we need the lamp to be driven so that we can check these resistances, because otherwise in a totally dark situation, these would all be very high mega ohm values. All right, and then turn on and check the value of the photoresistors at the pins listed in the table here. So I've already got the unit powered back on. So we're going to start with the photoresistor values here. So for V1, we need to go between pins 9 and 10. So pins 9 and 10 are going to be these. This is pin 10 here, so 9 is there. So we'll go ahead and hook our meter up to pins 9 and 10. And we see on the ohm meter there, we've got a value of 20 kilo ohms. And the resistance value should be 30 kilo ohms. So I'm going to make a note of that. So 20 kilo ohms. Now, there is one thing to keep in mind here is that you need to allow a tolerance of plus or minus 20% on the values. So 20% of 30K would be, plus or minus 6 kilo ohms, right? So, you're looking anywhere from 24K to 36K on this value. So this one's a little bit low, out of band. So we'll go ahead and proceed on. We'll get all the readings here, and then we'll look at what we need to do next. So we'll go to pins 2 and 3 on our A6 module. All right, and so pins 2 and 3 are here and right there. And we see we have a value of 28 kilo ohms. And 28 kilo ohms, so that should be 15 kilo ohms on that one. We'll go ahead and do the next one. We need to go across pins 1 and 10. So we'll go again from pin 1, which is going to be all the way here on the end, and pin 10, which is down there on that end, and we get a value of 21 kilo ohms. So a little bit closer to where we need to be, but I still don't think that that's going to be within the 20% tolerance. Now the last two photoresistors, V4 and V5, are a little bit larger, 150 kilo ohms each. So we need to go across pins 3 and 4. So we'll go across pin, so this is 1, 2, 3, and in this, as you can see, there's actually a solder or a trace there on the board. So these both pins are these considered, both of these are considered pin 3, and so we'll go pin 4 and pin 3, and we've got a value of 117 kilo ohms. So we've got 117 kilo ohms, which again I believe is going to be out of spec, and our last one is going to be from pins 5 and 10. So we'll take our last reading here, and we'll go again from pin 10, which is down here on the end, to this is 3, 4, and 5 right here, and we've got a value of 120, we'll call it 125 kilo ohms there. So that one actually will be in spec for our plus or minus 20%, because plus 20% will give you 30 kilo ohms on either side of 150, so 120 to 180 kilo ohms. So that one is actually in spec, albeit it's going to be right at the very bottom of what's allowed. So what it says, so we can see that all of our resistors, well, at least 4 of the 5 photoresistors are out of spec here, and one of them is pretty low. It's going to be questionable as to whether it's working right. So if any resistance value is out of tolerance, refer to paragraph 548. So if the resistor adjusted, we'll need to do the bridge balance adjustment in paragraph 530. We'll go back to that later. So what you're going to do is you're going to remove the A6 board and adjust the resistors. And the way you adjust them is you reposition them. So if resistance is high, move the photoresistor closer to a light source, and then if it's low, then you move the resistor away from the light source. So it's a pretty crude adjustment, and it's probably going to be a lot of fiddling around to get these adjustments made. And then after you reposition the photoresistors, put it all back together, plug it back in, and then reperform the measurements and see how your results are showing. All right, so in order to get the A6 assembly out, it's pretty easy. We've already got most of it disconnected here. We'll go ahead and pull the power supply leads. I've got the unit turned off now, so there's no power in it. So we'll fully disconnect that. And there's one screw that needs to be removed, and it actually has a cutout right here through the A3 board. So you can just remove that one screw, and then the whole assembly will come out there as a whole unit. All right, and here is our A6 assembly. As you can see, there's not really a whole lot to it. It's just, a board inside this little plexiglass, or I don't know, it's probably phenolic or some kind of enclosure here. So what I think I need to do, all right, so I've got the values written down here on the board, or on the this sheet here from our numbers that we took here when we did our resistance checks. I just copied them over onto this sheet here for a little bit of clarity here. So our V1 is supposed to be 30K, and then our band is 24 to 36, and on 15 and 15, and then the band is 12 to 18K, and then the 150, the band is 120 to 180K. So that's our plus or minus 20% value there for these values. And here's what we actually measured, so we can see that we're out of band on all but one of them. So what the manual says to do is to move the photocells, and if the resistance is low, but it's not, it's the resistance is high, which is what it was. So well, let's see, let's say that again. So on V1 the resistance was too low. So if the resistance was low, then move the photoresistor away from the light source. So for V1, which is this one right here, we would need to move that photoresistor away from the lamp. So we'd have to sort of push it back a little bit. I think what we're going to do is, let's see if we can get this V1. Let's see if we can get that one first. We can get one of them eliminated, and then we can work on this other assembly here. So I'm going to focus on this one first. So we need to move this. That one was low, so I'm going to see if I can move that a little bit closer to the lamp assembly there. So I suspect that I'm going to be in and out of this module quite a bit here, so I'm not going to keep putting it in and out of the unit. So all I've done is I've just got a couple of jumper leads from the lamp driver leads, which are right there, clipped into the leads here so that I can take measurements without having to go in and out of the unit there. All right, so let's power it on and see what we get here. So we turn it on and we see that, all right, so now we've got a good adjustment. So we're reading 29.5 kilo ohms. So it looks like that that resistor is adjusted correctly. Now we're gonna have to go with the more difficult task here of getting the rest of these. So these resistors here were all reading low, or I'm sorry, these were reading high, which means we need to bring the lamp, the photocell closer to the resistor. But as you remember from the what we looked at a minute ago, all of those photoresistors were pretty much dead on the lamp. Like they were already physically touching the lamp, so there's not really any way to get them closer. So what I think I'm going to have to do is replace some of these photocells. So I've got these photocells that I picked up online, and you know, it's a whole bunch of photocells here, and you know, they're the right kind of photocells, but I don't know which ones will necessarily work in this circuit. So I think I've got an idea of how I'm going to check this, and we'll see if we can find some photocells that give us the correct response here. All right, so I've got the lights in my lab turned off now, so it's pretty dark in here, and you can see the board, how it's lit up here, and that's the two those incandescent lamp drivers. And I'm going to show you something here. So I've got you know, the cover's off, and I've got just a little bit of light in the background there from my computer desk. But as you can see here on the voltmeter, we're still getting pretty close to what we had before. We had 29.5 kilo ohms there, and now we're reading 31 kilo ohms. So only about 1.5 kilo ohms higher, or I'm sorry, 1.5 kilo ohms higher, yes, than what we were before. So I don't think that this setup here may be good enough, at least to do some testing. And so what I plan to do is I'm going to use, I've got my pile of photocells here, and I'm just going to hook take the resistance reading of the cell and just bring it in proximity to the lamps there, and see if I can find some cells that will grade out to the right range for our A6 module there. And if we can find some cells that work, that we can replace, then we can remove some of these that are reading too high there and get this A6 assembly back working in order again. So I've graded out two photoresistors, these two here, and we'll put those in for let's see, it's a V2 and V3. We'll put those in. So those are our 15 kilo ohm resistors, and these two resistors graded out to just about perfect. So I set them up to the lamp there, and you know, about it was about maybe a quarter or 3/8 of an inch from the bulb, and they were getting right at 15 kilo ohms. So I think that maybe we'll put those in. Those will be the best guesses here. A lot of these, actually these right here were really low. These were down into the low, like 1 or 2 kilo ohms. And then some of these graded out, I think these maybe graded out maybe like 8 or 9 kilo ohms, and then varying up. And I think this one was the highest one, reading at maybe like 70 or 80 kilo ohms for this resistor here. But anyway, so we're going to put these two in. These are the other ones of these four here, also graded pretty close to these two, but I'm going to use I'm going to go with these two here. Take a look at our board here. As you can see, it's still powered up, and you can just kind of see how mounted those two photocells. So put them in there, and I'm trying to get focused on them. There we go. So you can see how they're mounted there, and I gave plenty of extra lead there, kind of cooled it up a little bit just to give it a little bit of ability to flex so we can position it. So the next thing we need to do now is take a look at these other two resistors, this V4 and V5. So they need to be 150 kilo ohms, and they're 117 and 125. So what I'm thinking that we'll do is I'll go ahead and just back. So that's these two resistors here on the outer sides here. So we'll back those out away from the bulb just a little bit, and that should get us the rest of the resistance we need there for that range. All right, one final look here at the insides of this assembly, and then we'll put it back together and we'll do our final resistance readings. It's all put back together in the black box there, and we've got the HP 334A powered on, and I'm going to have a look at our resistances. So I'm going to go through the photocells here. The first one is going to be V1. This is the V1, if you remember, is across pins 9 and 10, and that should read 30 kiloohms is the middle value of the acceptable range. And we see there we've got 29.8 kiloohms, so that is just fine there for V1. Now V2, this is one of the photoresistors that we replaced, is across pins 2 and 3, and it should have a middle value of 15 kiloohms. And we see that we've got 14.4, 14.5 kiloohms, or 14.45 kiloohms. So again, that's well within our range of 12 to 18 kiloohms for V2. V3, also one of the photoresistors that we replaced. I'm going to go across, that's across pins 1 and 10. And it should also have a center value of 15 kiloohms. And we see there that the value is, in fact, 15.1 kiloohms. So again, well within our range, our allowable range of 12 to 18 kiloohms. The next we'll look at is V4 and V5. Now these were the higher value resistors, and we didn't replace these, but we did have to do some positioning to get their values in within the correct band. So this first one, this is V4. This is across pins 3 and 4. And we see that we have a value of 147 kiloohms. So there are looking for a target of 150 kiloohms and a range of 120 to 180. So that is, again, well within the range that we're looking for. And the last one is V5. This is across pins 5 and 10. Again, looking for that 150 kiloohms, and we see there we've got 155 kiloohms. Again, same range of 120 to 180 kiloohms is the allowable range. So it looks like now we've got all of our photoresistors set up correctly, and we had to replace 2 of them, and we'll take a look at the ones that took out of the A6 assembly. These are the resistors that we took out. The ones that the HP resistors that we had in there, and you know, it's not anything too fancy. Now I did initially try this resistor in here for that was for V2, I believe. And what I found is that while this resistor showed a good value, it the resistance continued to increase as it stayed in circuit there. So while it started at 15 kiloohms, it climbed quickly out of range. So I don't know if that's a resistor, but I did notice that it's got a little different of an element. See, you can see this one. This is like the one that we put in for V3 and also V2. You see how it's got that kind of swirly sort of pattern in there, and this one's a little bit different. So I don't know if it's maybe a different construction or a different type of maybe a different type of doping on the resistor element there. But anyway, this one ended up not working, so took it back out and put one similar to this, so that V2 and V3 both have this type with that look. They look like that. Again, don't know. Sure, it's some kind of construction thing about that component there. But interesting note too that the ones from the HP ones also look like that as well. So these are the 2 that we removed. So now we're going to take this black box and put it back into the distortion analyzer. All right, our A6 board is back in and connected. Of course, I did. Once I reinstalled this A6 board, I went ahead and took resistance readings again, and I wrote them down on a sheet here. So we'll look at them to take a look. So these were the final readings out once with the A6 module installed. So again, we'll just look at these reviews. So for V1, we needed 30 kilo ohms, and the measured installed was 29.7 kilo ohms. V2, we need 15 kilo ohms, and measured was 14.5 kilo ohms. V3, we needed 15 kilo ohms, and the measured was 15.1 kilo ohms. V4 and V5, both 150 kilo ohms, and we got 148 and 153 on those. So all of those readings checked out good. So what we'll do next is we'll take a look at some of the other readings on the unit, and then we'll run it through, we'll start running through some of the performance checks and see if we can get to verify whether this unit is working correctly. All right, now because I know somebody's probably going to ask, because these are pretty popular units. This is the photocells, where I got the photocells from. There's the website there. I've ordered parts from them before. They work pretty good, but I do have to warn you that when you order these photocells from them, they just come as a mixed bag. So you may get lucky, or you may not. Just depends on what they have. Go and do some testing here. Let's just talk about real quickly about this wean bridge here and how it works, because we did, if you remember, we changed the photocells, some of the photocells that are part of this bridge for the automatic circuit. So let's look real quick. So we know that the wean bridge circuit here is what the manual says is it's only used in the distortion function. And what it does is the wean bridge is used to tune out the fundamental frequency when we're doing a distortion test. Some information from the service manual. So in the distortion measuring operation, the wean bridge circuit is used as a rejection filter for the fundamental frequency of the input signal. And what it's done is it's placed as basically a coupling stage between the preamplifier and the bridge amplifier circuit. And so it's because it's doing that coupling function there. When the bridge is properly tuned, it should remove all of the fundamental frequency that we're using for doing our distortion measurement, so that at that point, once that's done, the only thing that should be left going into the bridge amplifier would be whatever is left that's not part of the fundamental. So that would be all of your distortion products. And then we could use the that product that's left over. We can quantify that and take a measurement for determining distortion level. And then so the way that happens is there are basically two legs of this bridge that are tuned, and I say two because I'm gonna group these two legs together because we essentially tune these at the same time, and then we do a separate say tuning. Really, it's a balance on this leg here. So we've got we'll talk about these two legs here. This leg over here is a fixed single resistor component. It's not going to change, but this leg here, which is our balance leg, is what they refer to as the resistive branch. And then these two legs here are what they call are the reactive branches. And more specifically, we have a series reactive leg and a shunt reactive leg. All right, looking back at the service manual here, the bridge is tuned to the fundamental frequency of the input signal by setting the frequency range selector S4 for the applicable range, and then we adjust tuning capacitor C4 through C4A through C4D. And that's what this is showing here. This simplified schematic here, these variable capacitors are representative of C4, and then these resistors here are they're shown as variable resistors, but in reality they are a frequency selection network of the frequency range switch. So we'll look at the schematic here, and that's what we see here. So we've got our C4 tuning capacitor network here, and we've got our range selector switch here, and we can see that depending on the range will switch in various resistance values. And I've went ahead and further kind of broke it down into some more of like a bridge type arrangement. And we can see that these resistors that I have circled here are the frequency range selection network, and our capacitor C4 shown here. And then the final component that we'll talk about, and we'll get to that in a minute, are these photocells, V4 and V5. Of course, all these components are shown for the 1x scale. I didn't draw them out. I sort of made this drawing here more complex than the simplified drawing, but I didn't want to make it as complex as this drawing here, so it's sort of in between. But of course, these photocells will change depending on when we get up to the higher ranges. We'll switch in V3 or V2 and V3, which are, if you remember, are the photocells that we actually swapped out with new ones. So anyway, back to the bridge circuit here. Our two reactive legs, and then our other leg, which is our resistive leg here, and incorporating a V1 photocell as part of the balance leg here. All right, so we've talked about the components here. We said so when we tune C4A through C4D, the bridge circuit is tuned, and then the bridge circuit is balanced by adjusting the coarse balance control R4 and the fine balance control R5. Now, that's if we're doing a manual bridge balance. But if we want to do an automatic bridge balance, which is what we want to do, because the automatic control can get much finer control over the bridge balance and then maintain that bridge balance if our frequency, our fundamental, starts to drift at all. So the automatic mode is a fine-tuning mode, and that's balanced by using photocells. And of course, you know how a photocell works. It's driven by the resistance is dependent on a light source, and the light intensity in this particular arrangement is controlled by the reactive and the resistive control loops. Now, the manual goes on to explain what happens if the bridge is not tuned properly. To summarize, what happens is if the bridge is balanced, if the bridge is tuned but not balanced, then a portion of the fundamental will be detected on the output of the bridge, and that fundamental, or that portion of the fundamental, is in phase with the fundamental, and the control loop recognizes that it's in phase. It actuates the resistive control loop to bring the bridge back into balance. If the reactive leg is not in balance, but the resistive leg is in balance, then again we get a portion of the fundamental coming out of the bridge, but that portion is out of phase with the fundamental, and the circuit can detect whether that it's out of phase, and it knows to use the reactive control loop. And that is what this verbiage here talks about, and what they're trying to explain here with these drawings. Now, what they also talk about too is if you were to, as you adjust the balance, your output, which is this represents this is the fundamental, the input, and these graphs B and C represent the output of the bridge. If it's not tuned, we get a smaller portion of the output signal, and as you make an adjustment here as we bring the resistive leg into balance, this signal will get smaller and smaller and smaller until when it is balanced, it should be at 0. And if you continue to make adjustments, then it would go unbalanced, and it would be 180 degrees. It'll be 100 degrees out of phase with the fundamental, which is shown here. Now, the phase relationship is important because we talk about what it looks for is a 90-degree phase differential for whether it's the resistive or the reactive leg, and that's what this is showing here. So then this drawing here, the reactive leg is shown out of balance, and we see that it's shown 90 degrees out of phase with our fundamental. And again, the same idea, as it gets closer and closer to being in balance, it will bring that down to 0, and then if we continue to make adjustments in that same direction, it will then go out of balance but again, be 90 degrees out of phase with our fundamental. And that's what we see here on our overall block diagram. So we see that we've got our control loops here, our 90 degree phase lag, and our phase detector here. This will be for the reactive loop, and then again sensing and providing that sensed input to our phase detector and lamp driver for the resistive branch. And it also looks at the output. So this is how it gets determines. So this would be our our reference signal here, and our error signal here on the output of the distortion analyzer here. So we're comparing our reference to our error signal, and then those are used to drive the control loops to bring the bridge into balance. And like I said, the circuit is smart enough to determine whether it's the reactive legs that are out of balance, or the out of adjustment, or the resistive leg, which is out of adjustment, by looking at the phase relationship of the fundamental, or the signal compared to the input signal. So we're using a bridge circuit here, and looking at this page here from the service manual, again, talks about sort of how this Wien bridge, the rejection characteristics here, and they got a response curve here for the bridge circuit, and you can see that for our fundamental frequency, which is what's shown here, what we do is we move this point when we tune the bridge. We move the notch of this curve up and down this frequency chart here. Over here, we see that the relative attenuation. This is in dB values here. This, when tuned for a fundamental, this would have a very deeper rejection factor for that fundamental frequency, and that's how we're using this Wien bridge to remove the fundamental. Now, it's very wide here. You can see how it's very wide, and this is not ideal, because you don't want a lot of attenuation for other frequencies. You want just really only frequency you want to get rid of is the fundamental, because ideally, if you think about it in an ideal situation, if you apply a 1 kilohertz pure 1 kilohertz sine wave to an amplifier, and or whatever you're testing, and that output, that device that you're testing, should produce a pure 1 kilohertz sine wave on the output, and it would have zero distortion. But if there's any distortion at all, then that distortion would manifest itself in the form of other frequency products at the output, and that's what we're looking for. So any frequency products that fall into this notch are not going to be measured. So they would be there, and they would be forms of distortion, but they wouldn't be measured by the distortion analyzer, and that's what we're trying to measure. So we can increase the accuracy of our distortion measurement by tightening this notch and making it very narrow, and that's what they have shown here with the use of feedback in this bridge amplifier circuit. So we apply some of the output feedback back to the input, and that causes this notch to sort of get very narrow and very steep here, so that we have very little attenuation for any frequency component except for the fundamental that we're trying to reject. And that means that we're going to be able to detect more distortion products, so we'll get a better distortion measurement for whatever we're trying to test. And here, just from the text, sort of what we just talked about there, is when the bridge circuit is tuned and balanced, the voltage and phase to the voltage and phase of the fundamental, the output of the shunt reactive leg is the same as the midpoint of the resistive leg. And when these two voltages are equal and in phase, the fundamental frequency will not appear at the drain of a field effects transistor A3Q4, which is the input to the bridge amplifier, which is shown here on our schematic. And of course this amplifier is what then is used to drive our meter circuit here to ultimately give us an indication of distortion. I've done is I've gone ahead and put the unit back together, and you might hear the fan noise in the background there. I've got the spectrum analyzer hooked up to the output to monitor the output of the distortion analyzer. Because we're going to take we're going to do 2 readings here to check out this, to make sure this is working right. And so what I'm going to do is first I'm going to do a 1 kilohertz sine wave, and then we'll do a 10 kilohertz sine wave. And the reason I picked those is because so when we replace those 2 photocells as V2 and V3, if you notice on the schematic, those correspond to the X1K and the X10K ranges. Again, just looking down here, they respond to the X1K and the X10K ranges. So the X1, X10, and X100 ranges were not, those cells were not replaced. V4 and V5 we did not replace. We just had to adjust the positioning. So I want to go back and check to see if we get the proper fundamental rejection from our bridge, because that will tell us that this is probably more or less working correctly if we can get the appropriate rejection from the bridge circuit. All right, so looking at the performance test card, it says our fundamental frequency, our fundamental rejection should be greater than minus 80 dB. So when we put a fundamental in, and I guess we'll use 500 hertz and 5 kilohertz, or we'll do 500 hertz, and we can do 5 kilohertz since that's there, and we should get a greater than 80 dB rejection of the fundamental frequency, and that's assuming that there are no distortion products in our fundamental, and that's the key. That's the whole crux of taking the distortion analyzer or a distortion reading, is you've got to have a very good test signal to put in. Otherwise, you start measuring the distortion of your test signal that you're putting in, and not necessarily all that distortion is due to whatever you're testing. So what I'm going to use is my HP 3325B. It's just straight going in. I don't have any filters or anything hooked up. So we're going to just do a measurement to see if we can get that 80 dB specification there. All right, so I'm going to set my function gen up here. We'll go 500 hertz, and we're going to amplitude of 1 volts RMS. All right, so first thing we'll do is we'll set level, and what it's going to tell you to do is set this up for a 0 dB indication there on our meter. And I've just got to see what we got hooked up here. So this is coming in from the signal gen. It's terminated to 50 ohms because that's the output of the signal gen up there. And got the output of our distortion analyzer, feeding it through a T, going up to the oscilloscope so we can see the distortion products, and feeding into my spectrum analyzer here, and we'll need to change the center frequency to 500 hertz, and we'll keep the span 250 hertz, so that'll be good. All right, and so we'll note when we first get this set up, we note our initial reading there, and it looks like these are maybe a couple clock cycles off there, but that's close enough. So, all right, but the important thing to notice is our reference level, our reference, which is negative 9.6 dB signal coming in, and that's because if you read in the service manual, this is a 0 to 0.1 volts. This is basically it's basically 10 dB down from whatever you're putting into here. So if I'm putting in so like say if I was putting in a 0 dB signal here, then I would get a minus 10 dB signal out here. So there's a little bit of internal attenuation here from the signal. But anyway, we just gotta keep that in mind. So that's going to be our initial reading there for taking this fundamental rejection reading. All right, so we've got this set up, and we'll go ahead and make sure that our controls are balanced. We need to set this on the, we'll set it on the 100x range, and we'll go ahead and put this at 5. All right, 5 there, because we're doing the 500 hertz. So, you know, just 100 times 5 is 500. All right, now we're gonna put in distortion. So we're gonna switch this over to distortion. And first thing we'll do is we'll tune the bridge down. And what we'll have to do is we'll have to continue to downscale here. All right, and then once we get to the bottom there, then we'll go to the balance the resistive side. And this one starts getting really jumpy down here as it starts getting towards the bottom. And then once we get to there, I'll make the little fine adjustments there. All right, so that looks like it's about adjusted. And we'll put this in automatic. And that should continue to drive down our reading there. All right, okay, so now we'll take our, all right, so now we got our distortion reading. And what we're gonna do is we're gonna look at, it's gonna be a combination of the switch setting here, plus what we see on the spectrum analyzer. So on the spectrum analyzer, I haven't moved the cursor, but as you can see now, we're at still at 500 hertz, but now we're down. We'll call it down minus 42 dB, and we'll call it. We'll look and see what this update is right here. Okay, there we go. So minus 48 dB, 48.3 dB. So we had minus 48 dB on the spectrum analyzer, and we're looking at minus 50. So this is minus 50 right here. So we're looking at minus 61, minus 61 dB on the meter. All right, but we got to add in our reference. We took initially, so we initially started at negative 9.6. So we'll go, let's see, we'll go 48 minus 9.6. So that was our actual change in on the spectrum analyzer. And then we take our switch setting, which was 61 dB. All right, so we'll go 38, and we'll add that to 61. All right, so 99.4 dB. So our specification there of greater than 80 dB, we got 99.4, and that was on a say that's probably on probably about an average update. I've seen it bouncing anywhere here from minus 40 to minus 60. So I'd say 48 is probably about the average there of what we're going to get. So there's a minus 54 right there. All right, and then you can see here is our residual product. We measured the, let's see, we did that. That was on the 100x scale. So right here in 100x. So let's go down and try to take a reading here with one of our new photocells. This is going to be on. So we're going to do a 5K, so it'll be on the 1x, 1kx scale. All right, so we've got changed now. We've got set up for 5 kilohertz, and we'll see that on the oscilloscope up there. and go ahead and put the, I basically put the analyzer back into sort of like a pre-measurement state here. So we're back at set level. We're on the 1kx scale now, and I've got the spectrum analyzer set up now for a reading at 500 or 5,000 hertz, 5 kilohertz there. And we see we got our reference level again about 9.7 dB, so about where we started a minute ago. And this is already pretty much adjusted for 0 dB. We'll go ahead and set that. And it doesn't look like it's made much change there. We'll let it update there. Yeah, we got 9.7 dB. It's going to be our reference. So we'll do the same thing again here. We'll go ahead and put this into distortion. All right, and let's see if we're balanced out. So we'll get the frequency dial first. Looks like that may already be pretty close to where it needed to be. Yeah, I'm getting a whole lot of response there. We'll do the resistive side now. Get a little more response out of. All right, and all right, so that's bottomed out there. We'll put that in automatic. All right, I'm just going to continue to drive it down just a little bit there. Okay, and so now we'll take a reading here. So this has gone out. We can see on the oscilloscope there, we've got our distortion products there on the oscilloscope. And we'll let this spectrum analyzer do an update here. All right, so we're at negative, we'll call it negative 41.5 dB. So again, remember we started at 9.7. That was our starting, and we said negative 41.5. So we'll take the difference of those numbers. I'm just going to punch these in the calculator. So the difference is 31.8 dB. And we are looking at our range here, negative 50. We got 50. So that's negative 61, 2. We'll call it 60.2. Not 60.2. We'll call that 62.5 dB. So, and then we'll punch those numbers in, 62.5 minus, or 62.5 plus 31.8. So that was our difference. So we got 94.3. So our fundamental rejection there was 94.3. All right. Fundamental rejection at 500 hertz and 5 kilohertz. We had, I think it was 99 dB of rejection there at 500 hertz, and at 5 kilohertz we had 94 dB. So that's pretty good. So I think this is working out. This is going to work out good. I'll go ahead and do the rest of the fundamental rejection measurements, and we'll go from there. Okay, and here is the results of our fundamental rejection check. So as we can see, the first two we did there on the video there, and then I went ahead and did the 50 kilohertz, 250 kilohertz, and 600 kilohertz measurements there. And here's our results. Total rejection there for the 50 kilohertz was 87.9, so a little bit closer to the limit of minus 80. And of course, these are all, I just dropped the negative to make the math easier, but essentially what you do is you add these two numbers here and subtract out your reference level, and you get the values there. So this is of total rejection. We got 87.9 dB of rejection on the 50 kilohertz, 91.2% 91.2 dB of rejection on the 250 kilohertz, and then just squeaking in on the 600 kilohertz fundamental rejection test at that 82.1 dB of rejection. So just barely making that minus 80 dB of rejection requirement. And one thing to note too, the high pass filter for fundamentals greater than 1 kilohertz. I played around with that when I was taking these readings. It really didn't have too much of an effect. And if you read the manual, what it talks about, this filter says it has very little attenuation effect above 1 kilohertz. But what it does is if you are taking if your fundamental signal is greater than 1 kilohertz and you put this filter in, it has a lot of rejection for 60 hertz interference. So you can put that in and that will cut down on your 60 hertz interference on your measurements. But like I said, with the covers installed, I wasn't getting it, and of course we're using all the shielded coax and everything, so I wasn't getting a lot of interference there. But like I said, I did play around with it and noticed that it really didn't measure, or didn't really make much of a difference here. As you can see, I'm still set up for the 600 kilohertz fundamental check, and you can see there we got what was that, 58.5 dB of signal there, and the spectrum analyzer is still going there for 600 kilohertz. All right, so unfortunately this video is running pretty long, and I've got some more things I want to cover. So I'm gonna just sort of wrap up this portion here, and then if you look for the next video in this series, we'll actually take a look inside the unit. I've done some more work to it, and I'll explain what's been done on the inside here, and we will take a look with the oscilloscope, and we'll see how that bridge circuit is actually tuning this distortion analyzer, how it's actually tuning in that in automatic mode, how it's tuning down for the distortion reading. So we'll take a look at that on the oscilloscope. But just real quick too, just wanted to have you have a look at this real quick here. This is the test that we just completed there, the fundamental rejection test, and it outlines essentially what we've done here in that test, and where it talks about here using the different frequencies for the 5 kilohertz and the 50 and 250 and the 600. Of course, it has you start the first one with the 500 hertz reading, and then it tells you how to make those adjustments in automatic, and then changing the scales. And then here where it talks about this note here, it talks about how the output, output signal on the output jacks here is actually developed, and how you can read that, and how that you need to add those two readings, the reading from the, what they say is the wave analyzer meter, which is, you know, what we used to might refer to for a spectrum analyzer, but that's where we took the reading from the spectrum analyzer, and we have to add those the readings. The total fundamental rejection is the sum of the 334A meter range setting and the wave analyzer reading. So, and we looked at that here when we did the additions here for the readings of our meter and our output on the spectrum analyzer. All right, but like I said, I'm going to wrap this video up for now, and I hope that you will stay tuned for the next part in this video series. Thanks for watching.